This tutorial is a brief introduction to acids, bases, and salts. So anything to do with Kw or pH calculations will not be in this video. Common acids include hydrochloric acid, sulfuric acid, nitric acid, phosphoric acid, and ethanoic acid. There are many definitions of what acids and bases are, but we'll be sticking with the Bronsted-Lowry definition, which states that an acid is a proton donor, meaning when one of these are placed in water, they dissociate to some degree and release H+ ions. We call these protons. This is because a hydrogen atom contains a single proton and an electron. When it becomes H+, it loses the electron and it's basically just a proton. So when sulfuric acid is placed in water, it dissociates into 2H+ and SO4 2-. Likewise, HCl dissociates into H+ and Cl-. When in water, these H+ ions don't like to hang around. They actually react with the water and form hydroxonium ions, H3O+. So the equation would actually be like this. You can see that in both equations, the acid has donated H+ ions. Moving on to bases, which according to the Bronsted-Lowry definition are proton acceptors, meaning they take H+ ions. There are two types of bases, soluble bases and insoluble bases. Soluble bases are the ones that dissolve in water and are also known as alkalis, and they release OH- ions in solution. We can see in this reaction that NH3 has gained a hydrogen ion, meaning that it's a base. Not all acids and bases are the same. You can get strong and weak acids and strong and weak bases. A strong acid is one that almost entirely dissociates in water. For example, hydrochloric acid dissociates into H+ and Cl-. The equilibrium lies well to the right, meaning most of the hydrogens in HCl is released as H+, making it a strong acid. Had this been a weak acid, the equilibrium would lie to the left, so that only some H+ would be released. And it's the same story with bases. In a strong base, such as sodium hydroxide, the equilibrium lies to the right, so almost all the OH- are released. And in a weak base, the equilibrium lies to the left, so very little dissociating takes place. Now, strength isn't the same thing as concentration. Here we have two beakers, A and B. Each one contains 4 molecules of HCl. In A, 2 of the HCl's ionize and release H+. In B, only 1 HCl releases a H+. Now A and B both have the same concentration since they both contain 4 HCl's. But since A contains more H+, it's a stronger acid. And the same concept applies for bases. Finally, when acids react with bases, you generally get a salt and water. This is a neutralization reaction, since you're producing water. The salt you get depends on the acid you're using. With nitric acid, you get nitrates. With sulfuric acid, you get sulfates. And hydrochloric acid gets you chlorides and so on. There are basically 3 main acid-base reactions you need to know. Metal oxides with acids give you salt and water. Metal hydroxides in acid give you salt and water. And metal carbonates with acid give you salt, water, and carbon dioxide. In the first reaction, we can have a metal such as calcium oxide reacting with hydrochloric acid, and the salt produced is calcium chloride and water. We need to balance the equation, and this is the Ionic equation. Click on the link above to watch the video on how to write Ionic equations. In the second equation, we have sodium hydroxide reacting with hydrochloric acid, producing sodium chloride and water. The equation is already balanced, and this is the Ionic equation. In the third equation, we have potassium carbonate reacting with hydrochloric acid, producing potassium chloride, water, and CO2. Then we balance the equation, and the Ionic equation is this. These Ionic equations are always the same. So whenever you react a metal oxide with an acid, you always get the same Ionic equation. And whenever you react a hydroxide with an acid or a carbonate with an acid, the Ionic equation will be the same.